Before we start talking about the Hess law, which is used to calculate the enthalpy of a chemical reaction, we're first going to learn about something that's called state functions. These are very important quantities, and one example of the state functions can be the altitude. So let's see why the altitude is considered a state function and how they can generally be described. For example, in this case, if we have two hikers which are going to this point A and they're taking two different routes. So hiker 1 is going on this route, going directly and fast to the summit of the mountain and then going down to this point A, while on the other hand the second hiker is taking a longer path, so it's going through this forest, maybe taking some rest, so just taking longer time and taking a longer route, but eventually getting to this point A. What is important here that at this point, once they are here, they are on the same altitude. So let's say this is the altitude, and the altitude does not depend on the route that the hikers have taken, but it only depends on the initial and the final state. So initially they are at this altitude and then now at this altitude A. So if we want to generalize the state functions, these are quantities that only depend on the initial and the final state of the system. They're not dependent on how the final and initial states have been achieved. Other examples of state functions are, for example, the pressure and the volume. So why is volume a state function? Because it doesn't matter if initially this bottle is empty and I fill half of it, or if it was full and I've taken out half of it, I'm still gonna get half a bottle of water. So volume is a state function. Same for the pressure. Internal energy is also a state function, and perhaps more importantly for our purpose here, enthalpy is also a state function, and we can use the same principle of the dependence of only final and initial states to calculate the enthalpy of a chemical reaction. And the way we can do it is we can looking at this example. So if the hiker first is going to the summit of the mountain all the way to the top, let's say this is the altitude 1, and then he's going down again to this point, and then he's climbing to this point, let's say B, and we don't know the altitude of point B, but we know the altitude of the summit of the mountain, we know this altitude, this height, and also this one. So what we can do is we can first add this, and then we can subtract this height, and then we can add this height, and we'll get the altitude of B. So let's say this is X, and this is Y, and this is Z. If I add X and Y and Z together, I'll get to the point B. The only thing that we'll have to pay attention is to the signs. First, I'm going to the point A, which means that the X, the height, will be plus here, then I'm going down, so Y is minus, I'm going to put minus here, and then Z is plus again. So if I do all of this together, then I'll get the altitude of the B. Now let's see how this is related to chemical reactions. For example, if we have a reaction of A and B and the products are C and D, and we need to find the enthalpy of the reaction, which is here, the delta H, and we don't have a direct way how to do it, which means that we cannot do it experimentally and we cannot use the enthalpies of formation, we can still go back to the Hess law and determine the enthalpy of this reaction, considering that we have given data for some other reactions that are starting from A and B, or A and B are products. Let's see how it will work. For example, if we put the energy level here, A and B, so this will be a different reaction going to, let's say, product X, and we know the delta H of this reaction, and also on the other hand we know that the X can on a different reaction give the products Y, and we also know that the product Y can undergo a certain type of reaction and get to Z, and we know that Z can give another product W, and then W can undergo a reaction and finally give these products C and D, which is our target, which is what we wanted to determine, the enthalpy of this reaction. So like for the mountains, if we know the X and if we know the Y and Z, the heights or the altitude of these, we add everything together, we get the B. We do exactly the same here. If I add the enthalpy of this reaction, for example, this is 5 kilojoules and this is, let's say, 8, and then we have this going down, let's say this is 3, and we can put a sign here, so it's -3 actually, and we know that here we have 4 going up and then here going down, and we can say that this is, the height is, let's say, -7, If I add all of these together, the delta H of the reaction will be the sum of the enthalpies of all these reactions. So I'll have for the reaction 1, 5, and then for the second one I have 8, and then I have here it's -3, it's an exothermic reaction, and I can add 4 here, and then going down 7 again. This will give me the total process, the total enthalpy of the reaction, which seems to be 7 kilojoules. And so if we generalize, we can say that the enthalpy of the reaction can be calculated from enthalpies of other reactions as long as we can find a way how to add everything together, all the other reactions, to get to the target product that we have here. As an example, suppose I need to find the enthalpy of this reaction, how the nitrogen oxide can be formed from nitrogen and oxygen, knowing the enthalpies of these two reactions. So when you're solving a Hess law problem, what you want to do is take a look at what is given. These are the reactions that are given to you. You have the data, and then you're looking at your target reaction, which is this, and you're trying to find a way how to add these reactions together to make the target reaction. So when we're saying add the reactions, you may need to reverse the reactions in order just to match the molecules, because remember, the hiker can go up, can go down again, and then up again. All that matters is that finally you want to get to this point A, which is the nitrogen oxide in this case. So if I'm looking at my reaction, the nitrogen dioxide is the product. And I'm going to look for the nitrogen dioxide in the other two reactions. It's not here and it's here. Well, here it's a reactant, but I want it to be a product, which means that what I need to do is I need to reverse this reaction. So if when I reverse it, the products and reactants will be switched. So I'm going to move the nitrogen monoxide and oxygen to this side. I'm going to write down that 2NO reacting with oxygen will produce 2 nitrogen dioxide. So when I reverse it, I need to change the sign here, because if the hiker is going up, it's plus. If it's going down, it's minus. So I'm going to write down that the delta H of this reaction is equal to -112 kilojoules. And so generally, these are just the two rules that you need to remember. If you're going to reverse a reaction, you also need to reverse the sign. If you're going to multiply the reaction by any factor, let's say you need 4 nitrogen dioxide, but you only have 2, then you need to multiply this by 2. You still need to multiply the enthalpy of the reaction by 2 as well, or any other number that you have. So really, there's just 2 laws that you need to remember in order to apply to the Hess law. Now let's check what we have. So if I add these two reactions together, so for a moment, we kind of forget about this because we don't need it anymore. So we have 2 reactions. Reaction 1, let's say 1, and we have reaction 2. So now if I add them together, this will be my product. And what I want in the target, I want the nitrogen and oxygen be the reactants, which are reactants here. So let's try to add these 2 reactions together. If I add reaction 1 to reaction 2, what I will have is N2 plus O2, the reactants. Now I'm taking the reactants from this side, plus 2NO plus O2. They're going to give me the products, and the products are here. So I have nitrogen monoxide, 2NO, and I have nitrogen dioxide. And the delta H of this is going to be the sum of the delta H1 plus delta H2. Of course, we're going to consider the sign as well. But before doing that, let's check and see if there are actually some extra molecules that appear on both sides of the equation that we can just leave out. Nitrogen monoxide, so you can leave this out. And so here you have 2 oxygens and 1 nitrogen. So if I just rewrite it slightly differently, I can say that nitrogen reacting with 2 oxygens is producing nitrogen dioxide, and the delta H of this reaction is the sum of the 2. So if I add these 2 together, it's going to be 100 minus 112 kilojoules, which is going to be equal to 68 kilojoules, and this is the enthalpy of my target reaction. So that's the idea. Anytime you have a problem with Hess law, you're going to manipulate this equation. You may need to reverse them, you may need to multiply by any number just to match the target equation, match the products and match the reactants, and then you also add the enthalpies.